Alrighty guys, so we are going to add today page 48 and 49, and we are going to look at nonlinear patterns. So, if it's not a line, it's not linear. So nonlinear patterns. And we're going to do it in much the same way that we were looking at our linear patterns, but for these ones, I'm a little less concerned about if we can figure out the equations or not. It's great if we can, but if not, it's not a huge deal for now. So if we turn the page to 48, we don't have anything on that one. On 49 at the top, we will write non-linear patterns. So nonlinear just means not a line graphically. So it might be like a curve, or it might just be random smattering of points, or might not even be a function. So just kind of depends. And then when we look at a table and an equation too, there are other ways to tell, but the big deal is it's not a line. So if we take a look at our duckies, same way we were doing the other one. In the first step, here I have 4 ducks. Then I have 8 ducks. Then I have 16 ducks. So if I try to think about adding the same number every time like we did for linear ones, I don't think that will work here, because 4 plus 4 is 8, but if I try to add 4 again, I don't get to 16. That's only 12. So, but I can tell that there is kind of a pattern here, because it's like 4, then 8, then 16. And so rather than adding the same thing every time, I feel like I'm timesing by something every time. Like if I do 4 times 2, that's 8. And if I do 8 times 2, that's 16. So rather than add every time, this time it seems like the pattern is growing by multiplying by 2 each time. And so that means there would probably be, so 16 times 2, that'd be 32 ducks in the next step. And if I times by 2 again, that'd be 64 ducks, and then it's starting to get real big. So just like we did before, we can represent our nonlinear functions as a table, equation, and a graph. So if we think about our table and we do step, and in this case, number of ducks. In the first step, I had 4 ducks. Second step, I had 8 ducks. Third step, I had 16 ducks. In the fourth step, it seems like I should have 32. And in the fifth, 64. And again, with this one here, we can kind of see a pattern that I'm multiplying by 2, multiplying by 2, multiplying by 2, multiplying by 2. So not the same idea as the last time, because that one was adding every time. This one is timesing every time. So that's a little different. We can also see it in the graph. So if I plot my points, I might not be able to fit all of them, and that's okay. We're going to fit as many as we can. So I'm going to plot 1, 4, and then 2, 8, and then 3, 16. Oh boy, I think this is one I'm not going to fit anymore. 2, yeah, it's like way up there. And I don't think I can get a straight line through all those points because it starts going way too fast. So what's really happening there is you are like shooting and taking off, and this is really a curve that is going quick, 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 quick. Okay? Now, when we thought about our equation, I wanted to do that in this color. Boop, boop, boop. For a linear function, because I was adding over and over and over again, the shortcut for addition, if I want to add over and over and over again, is multiplication. Well, if I multiply over and over and over again, there's a shortcut for that too, and it's an exponent. So because I'm multiplying 2 over and over and over again, you might think that it's like to the second power, but that isn't actually the case here. And again, like, don't worry too much about the equation. The equation for this one would actually be 2 to the x power. And the reason that that would work out, well, and it doesn't totally work out. I think I have to multiply by something. Because if I put in 1, 2 to the first power is 2, and that's not 4. And if I put in 2 to this, so I think I need to times this also by 2. Because if I do 2 to the first power, that's 2, times 2 is 4. If I do 2 to the second power, that's 4, times 2 is 8. If I do 2 to the third power, that's 2 times 2 times 2. That's 8, times 2 is 16. So that would be my function here. And I can tell that that's not linear because x is up in the exponent, which is not supposed to happen when it's linear. Now, if you feel super scared about writing your own equation, it's really okay. You can try, but you don't have to. If you can't get it, just say, like, I can't. Let's try another. So if we open this up, if we want to take a look at how many squares we have. So in the first one, I have 1 square. In the next one, I have 4 squares, just the little squares. Don't count all of them. And then in the next one, I think I have 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. And so if I think about trying to add the same thing, because it's getting bigger, I added 3 and then I added 5. So not linear. And I don't even think I can multiply by the same thing every time like I did on the last one. Like 1 to 4, I'd have to times by 4, like 1 times 4 is 4. But then I'd have to do 4 times 4, which is not 9. So I don't know. Like, this one's tricky. I'm going to make my table because sometimes if I see the numbers in a row better, I can guess what the next one will be. So if I write out this step and then number of squares. So on step 1, there's 1 square. On step 2, there are 4 squares. On step 3, there are 9 squares. So I need to try to make a guess. Well, if I think about adding, when I went from here to here, I added 3. And then I added 5. So maybe the next one would be like add 7. Because it's like going up by 2. And so that would mean that this one would have to be 16, which if we look side to side, like that kind of makes sense. And then for step 5, maybe it would make sense that the next one should be like add 9, because it seems like we're just increasing this by 2 each time. And so that would mean that this would be 25. And so the pattern is growing where it's kind of like adding 2 away, like you're adding all the odd numbers, I guess. Or like another way to think about this too is if I think about how the pattern itself is growing, like what I'm adding by, that's up by 2, up by 2, up by 2. So this pattern is growing. And there's a couple of things you could say here. We are adding odds each time, or the pattern itself is going up by 2 each time. And so how many squares in the next step? That would be 16, and then we had 25. And so if we think about the graph of this guy, if I plot the points, we had 1, 1, and then 2, 4, and then 3, 9, 1, 2, 3. And again, I can see that this is jumping quicker, quicker, quicker. And then 1, 2, 3, 4, 1, 2, 7, 8, 9, 10, 11, 12, 13, 14, 15, off the graph. And I don't think I can get a straight line through that. Again, I think it's kind of a curve. It's going up, quick, quick, quick. And now this one isn't even like the last one. The last one, I was timesing the same number each time. This one, I am kind of adding in a pattern, but that pattern doesn't show up until the second time around. So this equation, again, is not one I need to be super scared about, but this equation, because it took me 2 tries to add the same thing each time, because try 1, they weren't all the same, but on try 2, they were all the same, that one would be x to the second power. And so if I think about how my function works, if I plug in 1, 1 squared is 1. If I plug in 2, 2 squared is 4. If I plug in 3, 3 squared is 9. And if I plug in 4, 4 is makes sense, hopefully. So how to tell if it's nonlinear. So if I'm looking at a table, I will know that it's nonlinear if a couple of things happen. So maybe if I multiply the same number each time, or divide. Or if it takes me, so if it takes 2 or 3 or 4 tries to get an adding pattern, like this took me 2 tries to get an adding pattern, or if there's just no pattern. That could happen. There's just no pattern. I can tell from the equation that it's nonlinear if it has an exponent. So if it has an exponent or power, or like the first one we had, x itself was an exponent. So if it has an exponent, I feel like both those apply, or if x is in the denominator. That would also be bad. And I can tell from the graph that it's nonlinear if it's a curve or just scattered. So alrighty, so let's jump in and do another homework problem together. So if we take a look, boop, and we go to our nonlinear patterns, same idea. So if I do this first one with us, we have the rabbits here. So first we had 3 rabbits. I gotta write this down. Then we have 9. Oh my gosh, and then we have a whole ton. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 rabbits. Oh my word. But it does seem like, so 3 to 9, 9 to 27, it seems like we're timesing by 3. So multiply by 3 each time, which then if I did 27 times 3, ooh, that's going to be big. 27 times 3, that's going to be what, 71? Oh my God. Siri, help me. Where is she? Oh my God. You guys probably already know it before me. 27 times 3. 81. Oh my God. Oof. And then if I times that by 3 again, that one's easier. 243. Not that you necessarily need it. Now the equation, this was like that first example we did where when I times by something every time, whatever number that is, I am raising that to the x power. So this would be something like 3 to the x power because we're timesing by 3 each time. And we might have to add to that. So let's kind of do our table. So we got 1 and we had 3 bunnies. And then 2, we had 9 bunnies. And then 3, we had 27 bunnies. And then 4, we had 81. And 5, we'd have 243. And so if I think about plugging that in, Oh yeah, I think this works out perfectly. So if I do 3 to the first power, that's 3 bunnies. If I do 3 to the second power, that's 9 bunnies. So that's great. Now with this one, guys, I wonder if we have a draw tool, because like I didn't think this through. We can try to insert a curvy line. Let's try it. Let's see how this looks. So if I plot that first point at 1, 3, and then I plot another one at 2, 9, so 3, 4, 5, 6, 7, 8, 9. And then I try to go again all the way up to 27. That would be like way up here. And you can see, oh my gosh, now I got to click again, I think. That is not a straight line. It's curvy. I'm going to leave it. I don't care. I love it. Oh, and we got it all. Okay, that's perfect. Awesome. Hopefully that kind of makes sense. And you guys got 3 more to try. If you need help, let me know.